So, in this lecture, we will discuss about the properties of flexibility matrix and the formation of flexibility matrix. The elements of flexibility matrix is actually displacements, otherwise called as flexibility coefficients. Then the order of the matrix is equal to the number of redundant forces. That means the degree of static indeterminacy. So, for example, if the structure has statical indeterminacy to second degree, then your matrix size will be, this flexibility matrix size will be 2 by 2. This is a square matrix, that means you will have always the size n by n. And the diagonal elements are always positive. So, based on Maxwell's reciprocal theorem, the flexibility matrix is a symmetric one, and it is valid only for stable structures. That means, if you are trying to formulate flexibility matrix for unstable structures, then the determinant of that matrix will be 0. So, for only for stable structures, you can formulate flexibility matrix. In each element, small del ij indicates the displacement at coordinates. So, delta ij indicates the displacement at coordinate I due to a unit force at coordinate j. Then to develop the entire flexibility matrix, a unit force should be applied one by one, that is successively at coordinates 1, 2, etc. and the displacement of all the coordinates are computed. That means, if you apply a unit load at coordinate 1, then you have to measure the displacement at all coordinates starting from 1. And we have to keep in mind that while applying unit force on the entire structure, we will have only that force. There is no external load, there is no other unit forces at other coordinates. Only one unit force at the particular coordinate. Then formulation or formation of flexibility matrix and the compatibility equation. So, using the principle of superposition, definition of flexibility matrix and law of compatibility, the final displacement at coordinate 1, that is delta 1, is equal to small delta 1 1 into P1 plus small delta 1 2 P2 plus up to small delta 1n into Pn plus delta 1n. Here, capital delta 1 is the final displacement at the coordinate 1. The small delta 1 1 is nothing but the displacement due to the unit force at coordinate 1. That is, the first index 1 indicates where we measure the displacement. The second index indicates where we apply unit force. So here delta 1 is nothing but the displacement at coordinate 1 due to the unit force at coordinate 1, which is multiplied by the redundant force acting at coordinate 1, that is P1. So actually this is the displacement contribution towards the coordinate 1 by redundant force P1. Similarly, all other terms, that is delta 1 to P2 is the displacement contribution towards the final displacement at coordinate 1 by the redundant force acting at coordinate 2. Okay, likewise all other redundant force contribution is, and all contributions from the redundant forces are summed up. At last we sum up the displacement contribution towards coordinate 1 due to external loads or applied loads. All applied loads, not a single load, applied loads acting anywhere on the structure, but the displacement is measured at coordinate 1. Similarly, we can formulate the final displacement to other coordinates also, like this. Therefore, we can put in matrix form everything, that is delta is equal to, capital delta is equal to small delta into P plus capital delta L. Here capital delta is nothing but the final displacement matrix. This is the delta into P, the product of delta, small delta matrix and the P matrix is the displacement due to redundant forces, and final capital delta L is the displacement due to applied load. Here P is nothing but the redundant forces, small delta is nothing but a flexibility matrix. So from this expression we can derive the value of P, redundant force, that is P is equal to delta, small delta inverse into capital delta minus capital delta L. So if the redundant force is either horizontal or vertical reaction, then the corresponding deflection is actually the flexibility coefficient. If the redundant force is a moment, then the corresponding rotation is actually the flexibility coefficient. So this procedure produces a set of compatibility equations equal in number to the redundant forces. That means one compatibility equation for redundant force, a single redundant force. Suppose if you have two redundant forces, then you will get two compatibility equations. Once redundant forces are solved using the expression, the above expression, that is P is equal to small delta inverse into capital delta minus delta L, then the remaining forces can be determined by equilibrium equations. So this is the end of the lecture.